Hi, and welcome to another video on interpreting graphs and making sense of them. We've looked at this graph a few times before. It's the halo cost based on time graph. But today we're going to take another look at it in a slightly different way. We're going to push what we've been doing with the generalization to a new bound. So let's start from the top. We've taken this graph already, and we've already said, okay, well, instead of y, we're going to say it's the cost. Instead of x, we're going to say it's the time. We're going to keep the 1.43, put the units on it. We're going to take the 49.1, put some units on it. And we get the equation that's on the board behind me. Now, let's talk about this. Let's really analyze this for a second. Because this isn't just the cost. It's the cost for Halo 3. And that's useful if I want to buy Halo. But what if I want to buy a different video game? Or what if I want to buy something else entirely that's not a video game? We'll start with just the video game first, but the idea can extrapolate outward. What if another one to know the cost for a video game? Any one video game. This could be anything from Bejeweled to the new Modern Warfare to Elder Scrolls 6, whatever it could be. We're going to keep some things the same, but other things are going to change. First of all, it's still going to be cost. It's still going to be measured in dollars. That's what you got to spend to get a video game. And we're going to still measure how it changes with time. But this $1.43 per month and this $49.1 are specific to Halo. This is the estimated cost for Halo at the start. This is how much Halo's value changed every month. And these are the parts we need to generalize now. So, what we're going to do is we're going to look at each of these individually and piece them together and start talking about how value changes, and then we're going to take this and apply it elsewhere. So let's start with the 49.1. If we look at the original graph, or think about this in general, 49.1 is here. It is the initial, or an approximation of the initial value. If you'd rather think about it a different way, though, at time equals 0, get rid of this entire center section here, what was the cost for Halo 3? Well, the cost was 49.1. What this tells us is that the initial value is both important and a factor. So instead of saying 49.1, which is just for Halo or just the approximation, what we can say instead is that that's representative of the initial cost or the initial condition. So this 49.1 is the initial cost. Okay, but what about this 1.43? We gotta go back and look at the graph. This 1.43 is the slope. It's representative of how it changes. Every month it goes down $1.43 over a month, down $1.43 over a month. If you look at 5 months, it's down 5 times $1.43 and over 5 months. The idea here is that there is a steady progression. There is a rate at which this occurs. And this idea of a rate is very key. So let's talk about that a little more in depth. So this is the rate Halo gets or a video game is cheaper at. So rate of deflation is a way to say that, or rate of cost decrease. And now I have an equation that can be used for any video game. If I know the cost it is now, if I know the initial cost and the time, I can find the rate of decrease. If I know the cost, the rate, and the time, I can find the initial cost. If I know the rate, the time, and the initial cost, I can find the current cost. What this does is it takes an equation that previously only worked for Halo But now we can solve for any video game, anything that devalues with time. In fact, I could just get cost for an item that devalues, and then we can watch it decrease. Anything. This could be cost for video games, this could be cost for a car, this could be cost for a computer, which gets cheaper as the technology slowly outdates itself. This equation no longer applies to Halo, it applies to any video game or object that really decreases in costs. What started with a set of data points gathered can now be generalized elsewhere. And while this doesn't seem particularly significant, we can use this general form to make predictions for many other facets, many other places. And the process we used here can be used almost anywhere else for generalization. So let's take a look at how this works, and then we're going to take it and apply it to somewhere slightly more relevant. Let's talk about the value of Control. Control is a video game that I very much enjoy, but it started at $60. It had an initial cost of $60. I saw it on sale the other day for $20. Control came out last August, a full year ago, but now it's a third of the price. What's the rate that's decreasing at? I don't have all the other data points. I can only find a singular rate. So what I can do now is, as opposed to using this number, I can find this number. Plug in the numbers I know. I said that it was originally $60. And I said it's been 12 months. I don't know the rate. I'm just going to abbreviate that to rate. But its current cost is 20 bucks. I can now solve for the rate. I subtract the 60 to the other side. 20 minus 60 is negative $40 equals rate times 12 months. And I divide both sides by 12 months. $12 over 12 months cancels out. 40 divided by 12 is $8.33. Right. And notice how we can do so much more with this. We can make predictions based on narrower sets of data about wider arrays of circumstances. By generalizing this equation from a set of data that was gathered relatively quickly, I went through a generalization process twice over, and now I can use it for anything. That's inherently powerful. Now, there are some issues here. I'm not going to lie. The first, and this is the big one, is that it assumes that the rate of decay is constant. Okay? The assumption here is that the rate is constant, which, while very useful for, let's talk about driving, which is what we'll do a lot of talking about, is very useful if you're going down the highway where you're traveling at a fairly constant rate, doesn't account for slowing down or speeding up. Let's say, for instance, Halo 3 comes out, and it's got a fairly steady decline, and then a new version of it, which happened, Halo 3 ODST, comes out. The original's price will really drop off much faster. So now let's talk about a different scenario. Okay, we've talked about this cost of video games, but let's take this and talk about cars, driving, right? So here we have a graph that relates distance traveled by a car, it doesn't say it, but it's a car, and the time it takes to do it. Let's do what we did with cost in video games and use it, the same general ideas, and use it to find out how to get a general equation. Okay? Start from the top. Y equals 3.6x minus 1.03. It's on the board, it's on the equation sheet. You can see it there. We don't need to zoom in quite yet. The important thing we need to do first is look at our units. Here, distance traveled is in meters. Here, time is in seconds. So we're going to need the two of those to make our... Also, our y-axis is distance, our x-axis is time. That'll also be relevant. Let's start with that, actually. So we said our y is distance. So the amount of distance this particular car, is from a measured point is 3.6 something times time minus 1.03 something. Okay? When we use our units, we know the 1.03 is going to be in meters because it is on the y-axis, it's the y value. The 3.6 is a little harder. It's a slope, it has units dependent on the change of the y versus over the change in x. Or it's going to be meters, which is your y values, change in y, over seconds, your change in x. This is going to be in meters per second. This is important. We just don't realize why yet. So now we have distance equals 3.6 times minus 1.03. For this car, we can have a general equation of how far it is from where we're measuring at a given point in time with these initial conditions. But we can go a step farther. Distance equals 3.6 times time minus 1.03 meters. What do these mean? We'll start with this. This is an initial value. This is a starting value. Your y-intercept is almost always an initial or starting value. In this case, it is the initial distance. Now, there's a couple ways you can write this. You can write distance initial. I inevitably will default to either using I for initial or far more often, because I spend way too much time dealing with calculus, I'll use this little 0. This little 0 here means not, N-A-U-G-H-T. It's a way of saying at time 0 or at the initial condition. Again, it's just a matter of parlance and comfort. If you see this, it's the same as me saying initial. It's just a habit of mine. The time stays the same. I'm going to shortcut this to say t, because physicists are lazy. They don't like writing letters. And lowercase t is the universal shorthand for time. Over here, I can still shortcut this over to d. The 3.6. The 3.6 is hard. It's a rate. We know that. It's a rate of change. It's a slope. We can know this because it's something per something. But what is that rate measuring? Well, think about it this way. Car starts here. After 1 second, it's gone 3.6 meters. After another second, it's gone another 3.6 meters. A common way you would call this the distance you travel in the amount of time, well, let's talk about it this way. What if these weren't meters? What if this was 3.6 miles, 7.2 miles? And you did this in a matter of hours. It would take you 1 hour to go 3.6 miles. Now that's a bad example, but the point still stands. It is a distance in an amount of time. You typically refer to that as speed. Now, the rate at something travels, the rate it covers distance and time, is referred to as its speed. In this case, we'll use that term. Distance in a car travels is based on how fast it's going, or its speed, times time. And what I can do here is instead of saying minus, we can say plus. Why? Because it's plus a negative value. Just because this is negative doesn't mean it's going to be negative all the time. It's just plus an initial value, whether it's positive or negative. Wherever it starts, if it's at positive 10 or minus 10, it makes how fast it goes from point A to B or how close it is from going along that depends on the time. Now, a few things. Firstly, I'm sure you're asking how do we have negative distance? Secondly, there's a problem with this graph and assumption. And thirdly, why do I care? We'll start with the first. How do you have negative distance? This is a concept that is really hard for a lot of people to understand in physics, but it makes a certain amount of sense if you think about it like so. So imagine you're on a street. Your house is here. You always measure everything with respect to your house. Okay? Going this way down the street is a positive direction. You call that positive distance from your house. So let's say 15, whatever, miles, meters down the road. The units aren't particularly important for this analogy, though they are important for the math. Is a friend's house. This is 15, say miles for current sake of argument. How far is it from your house to your friend's house? 15 miles. Easy peasy. But let's talk about that. Let's say you're not at your house. Let's say you're over here on your way to your house coming from school. You are here. How far are you from your friend's house? Well, that's going to be this initial distance here, this initial distance you are from your house plus the distance to your friend's house. Alternatively, if you were to head this direction from your house to your friend's house, it'd be positive 15. If you were to head this way from your house to you, it'd be negative. We call this way negative. So when we do the math for how long it will take you or how far you travel, it adds out properly. A secondary way to think about this. Negative distance just means you're behind your starting point. If I take a meter stick or a ruler and put it on the board, this is 0, this is 1. But as I count down, I go 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, and I keep going. I want to go to -1, -2, -3. A negative distance, all it means is that you've assigned a direction to be positive and you're behind your starting point. Second issue. This assumes a constant speed. This assumes you've got your cruise control set, which is great if you're on the highway or if you're coasting down the road. But the moment you have to stop or you run into a stoplight or you see a cop and you need to slow down because you're speeding, that's my problem. The idea that the speed changes becomes problematic. There's also this slight issue of, okay, which way's positive and what happens if I go, what happens if my friend is down the block and around the corner as opposed to a straight line? These are issues that we will have to deal with to really make this work. But for now, don't worry about them. We'll get to that problem when we get there. Don't make things harder than they need to be. The final issue is, why do you care? Well, I can give you the boring answer of because I said so. But if you want a more comprehensive answer, this process, this generalization idea, can be applied to anything. Once you find the patterns and the ideas in the world around you, you can start predicting what's going to happen next. Now, with cars and the such, that's kind of lame. Yeah, sure, if I step on the gas, I'm going to go that way. Whatever, Mr. P. But if you take this idea and extrapolate, okay, my fever went from 98 to 101. If I continue on this trend, in a few hours, I'm going to break 103 degrees. That will kill me. I need to do something now. If I can see where this trend is going, I can prevent a disaster. Or more positively, okay, how much money will I have in the bank if I set this aside and put it in savings? Or even better, this stock consistently has grown by this amount every month. If I invest now, how much money do I stand to make in 2 months? 4, 6, 8. It helps you predict the future. Or I eat breakfast at 6:30 in the morning, a little before actually. When do I need to eat lunch? Well, the rate I burn the calories tells me the rate I lose calories at, and it tells me when I'm going to start getting hungry, hangry, frustrated, and just be generally unpleasant to be around. Not only can I predict when I need to eat, I can also predict how much I need to eat to get me through time. Let's say I can't eat until 12, when my first free period is. I need to figure out how many calories I need to get me through to that time. Which tells me how big my breakfast needs to be. This idea, this process, can be extrapolated infinitely beyond the realms of math and science to any facet of your life. Now, we're going to focus primarily on the math because one, this is a physics class, and two, I understand the math better than anything. But the skills transfer. The ability to generalize and predict become incredibly useful no matter where you are. With that said, let's do one more practice problem on your own. Then we'll talk about some homework. Our first example is going to be using this equation that we just derived and seeing if we can't make some predictions. We're going to look at two separate scenarios that are unrelated but work the problem from different angles. The first, you need to go to work. Work is 1,500 meters from your house. However, unfortunately for you, you're not at house. You are 300 meters from your house in the opposite direction of work. Visiting a friend, picking up gas, whatever. The average speed, which is a shortcut we use to account for the fact that you're going to speed up or slow down. We'll get into the more nitty-gritty later, but your average speed driving to work is about 10 meters per second, which, given conversion, is about 25 miles per hour, safe driving through towns. How long does it take you to get to work? Other end of the spectrum. The distance from work for me to my house is roughly 30 miles. The distance I need to travel is 30 miles. However, if I start from my aunt's house, who's a little bit halfway between here and there, it's actually about 12 miles. From my house to my aunt's, and then another 18 from there to work for a total of 30. I have an easier time getting to work. I stop by and visit her about once a week. I decide to work late, or have to work late, and I need to get to my aunt's house for dinner. That's in 30 minutes, or half an hour. How fast do I need to drive on average? What's my speed need to be to make sure I make it to dinner on time? Go ahead, give this a try. Check back in after you're done. Pause now. Okay, here are your answers. On the left side, which is a separate problem from the right, I started by taking my equation and plugging in what I know. My distance that I need from my house to work is 1,500 meters. My initial distance is 300 meters. I'm at my friend's house. My speed is 10 meters per second. I plug in my numbers, and then the only variable I have left over is t, so I'm solving for t. Now, you'll notice that when I take this negative 300 and put it on the other side, I have to go a total distance of 1,800 meters, which matches my logic. 300 meters from my house plus another 1,500 meters beyond that is 1,800. The only reason it's negative is because I'm farther away from work, not closer. Add those two together, I get 1,800 meters equals 10 meters per second times t. Divide by 10 meters per second, divide by 10 meters per second, I get 180 seconds equals t. Notice, again, how the units cancel here. Meters, which is effectively over 1, divided by meters per second is the same as meters over 1 times seconds over meters. The meters on top and meters on bottom cancel, leaving me with seconds. This way, we don't have to think about units if we follow the units through doing the math. On the other end, work is 30 miles away from my house, but I'm already 12 miles closer. In this case, I'm already part of the way when I walked it through and described it. I'm already part of the distance I need to go. This is why this one's positive, whereas this one was negative. I don't know how fast I need to go on average, so I can make it to dinner in a half hour. So I once again start with my equation, I plug in my variables, miles, speed, 0.5 hours, miles. Subtract the 12 miles to the other side. Because they're the same unit, they can subtract, much like you could subtract x, 8x minus 5x, but you can't subtract 8x minus 3y. Once I've got this, I can divide, and I get miles over hour, or miles per hour. You're probably more used to seeing this written. Which is good for me, because I go down 31, which is generally 45 plus. Keeping an average of 36 shouldn't be too hard. Driving through some of the smaller, slower areas means I have to slow down, but I should be able to, on average, keep a 36. Provided I don't hit too many red lights, I should make it in time for dinner in a half hour without getting arrested. Follow? Makes sense. If not, ask questions, comments, concerns. Now let's take a look at a different one. Now you might recognize this graph from your homework or the last homework we assigned for the last lesson. What I want you to do is take the equation written up here and turn it into a general equation for this concept. The absorbance per concentration is a variable. You might have to come up with a name for it, but go ahead, turn everything here as best as you can into a word equation that is very general.